Hello, I'm Stacy Ross, and this is my presentation for Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to develop a better understanding of magnetic fields with respect to Biot-Savart's law. We will gain a better visual understanding of magnetic fields by experimenting with magnets and creating computational models. Biot-Savart's law gives an expression shown here that relates magnetic fields with displacement and magnetic dipole moment. Another important physics concept to note is the distance dependence equation. The distance dependence equation relates the magnetic field and distance. For this experiment, I used the following items: meter stick, tape, bar magnet, a magnetometer, and the Excel spreadsheet associated with this lab. For this experiment, I used the Teslameter app because it indicates separate x, y, and z components of the magnetic field and shows their numerical values. To begin, I found magnetic north by laying the phone flat on the table and rotating until the x component read 0. When the x component is 0, it's pointing in the magnetic north direction. Next, I had to find the magnetometer sensor location on the phone. I did this by moving the phone side to side and placing pieces of tape when I reached the intercept as shown in the diagram. Once I located magnetic north in the magnetometer, I proceeded to collect data regarding an on-axis dipole caused by the bar magnet. First, I found a distance from the magnet to the sensor that produced a magnetic field with an x component of magnitude 20 microteslas. I called this distance R20. I recorded the distance and the value of Bx in the spreadsheet provided on Canvas. I repeated this measurement twice for a total of 3 measurements of distance and magnitudes of Bx. The spreadsheet calculates the averages. Next, I repeated the procedure for magnitudes of 70, 120, 170, and 220 microteslas. I recorded the data in the appropriate locations in the spreadsheet. Next, I extracted a distance dependence equation from the data, which involves making a logarithmic plot of my observations. Assuming that the magnitude of the magnetic field due to the bar magnet is proportional to some constant times some power of the distance, I can write the dependence as B bar equals K times R to the N. I expect the magnitude of the magnetic field to decrease with distance, so N should be a negative number. From a plot of the electric field versus distance, it's difficult to tell exactly what the experimental value of N is. However, if I take the logarithm of both sides of the initial equation, I get natural log of Bx equals natural log of K plus N times natural log of R. Because natural log of Bx and natural log of R vary, but N is a constant and K is also a constant, this plot will give a straight line with slope N and intercept natural log of K. After inputting the data into the spreadsheet, it automatically produces a graph of the natural log of B versus the natural log of R. Thus, the slope is equal to N, which is equal to negative 3.329, and K is equal to e to the power of the y-intercept, which is equal to 3.66594 times 10 to the negative 7th. This information allowed me to create a distance dependence equation of B bar equals 2.695 times R to the negative 3.6659 times 10 to the negative 7th. Next, I calculated the magnitude of the magnetic dipole moment. Using the values we found and the Biot-Savart law, I found the magnitude of mu to be 18.33 ampere meters squared. After the experiment, I'm asked to select which statements apply and identify potential errors. The statement that applies are that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Some potential sources of error for this experiment are bumping the phone during the experiment, nearby electrical equipment, and the general inaccuracy of the app. Next, I created a computational model of an off-axis dipole using the general formula shown here. I experimented to find values that allow me to compare my computed field to real-life measurements at the same distance d. I inputted my data into the spreadsheet, making sure to correct the y component to account for Earth's magnetic field and repeating my measurements twice for a total of 3. Using the perpendicular distance and a program that implements the Biot-Savart law, I was able to solve for the electric field at the perpendicular distance. However, there is a bit of variation in the computational magnetic field versus the experimental magnetic field. Here you can see the respective magnetic fields for the computational versus experimental methods, both for a distance of 0.25503 meters at a 45-degree angle. The measured field has a smaller x and y component but a larger z component. This can be accounted for by the potential errors mentioned previously. If I hadn't oriented my experiment to compensate for magnetic north and had instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field, all of our values would be skewed north. This would result in inaccurate K, N, and mu values. If I were to stick two identical magnets together end to end and run the experiment again, all of the measurements would approximately double in magnitude but would stay in the same direction. That's all. Thanks for watching.